All right, so we're gonna get started. So the plan for today is we'll first finish what we had last time. So different variable types. So the model that we in the past so far is mostly about continuous outcome, how we model that. But as you went through all of the like either examples or maybe your own choice of the data set that you're going to work on for your project, you notice that definitely there are many other variable types out there that we should try to take care of. So we're going to cover, I think, for binary, for categorical, mostly for those two as an additional methodology to cover. Some of the methods you probably have heard about, some of them are probably new, so we're going to go through those. And just to refresh your memory, last time we talked about when you have multiple variables you want to synthesize, we talked about the sequential synthesis procedure. Okay, so right, so we can after talking about those different types of variable synthesis models, we're gonna just go back to the CLVD really quick to discuss some of the questions I posed on GitHub, and then we can move to each of you talking about what kind of data sets you're choosing for your project, and then like the demo of the risk that you have done so far, and then we can have a discussion there. Then we're going to move to the other topic for today is how to evaluate the risks, or evaluate the utility measures, the global utility measures, given the paper that we read before today. I know some of you are having trouble like figuring how to implement some of the methods, so we're going to try to cover those. Not that I have figured out everything, just so you know. So we might have questions and then discussions and all that. Okay. All right. So Bayesian synthesis models for different variable types. So for continuous variables, we talked about it. You can use a nonlinear regression model. We did that for the C sample. The demo that we did is only a single linear regression, but you can do multiple linear regression, like many of you did for the discussion for last time. So we're gonna skip that part. Binary variable, so they are binary outcome examples. I mean, there are many out there, including like if you're looking at a lot of surveys, they look at like labor participation, that will be a 0-1. And Eric's pretty like know a lot about this, loan default and all that credit risk modeling, and that's very typical outcome when you're looking at whether it's going to be a default or not for a particular loan or mortgage, and then that will be a binary outcome as well, yes or no. So many examples, and we're going to try to borrow the idea that we had for the normal linear regression. So remember, when we have continuous outcome, we try to model the outcome variable as a function of the explanatory variables. You might have multiple, you might have one. So we have to try to figure out how to do that for binary outcome. And you probably have heard about or worked on this type of models before. You're going to see that we're going to learn what we call logistic regression. That's also a regression model, but for a binary outcome. Right? So like the essence of that is still, I think, trying to figure out a way to model the outcome variable as a function of the explanatory. The linear, like the simple linear regression or multiple linear regression, is following the mean of the y's, right, as a function, as a linear function of the predictor. So here we will have to figure out something else, but still similar enough that we can borrow that kind of idea. So the outcome variable, let's use yi, either 0 or 1, and let's think of it as a binomial random variable. And I'm writing it in this way that yi, let's assume that it is independently following a binomial distribution with trial number 1, and then pi as the success probability. So binomial experiments with binomial random variables that we talked about actually was the first topic in 347 when we talked about it, when you're trying to model the success probability of some experiment, and then the outcome, like the sampling model that we did, is a binomial. But back then, I remember we're supposing giving a survey to a group of people, and then we're looking at how many people are going to say yes. And then, so that there is going to be a binomial of n. That's the how many people that you survey, and then p, right? But here, because the outcome variable is binary and is univariate, so we're looking at a binomial with trial count 1. So that's what that 1 is for. And then pi. So notice here we're using pi instead of p. because soon you're going to see that we're trying to model this P, which is the success probability, as a function of the explanatory variables. Okay, because we want to, like, say, if you think about it, yi, we're writing, so you know, remember this notation, IND stands for independently, and we're trying to link, like, or I should say, have a observation-specific success probability. So they're different from each other. Okay, and then using the subscript pi here, we'll be able to help us to create a function or create a way that we can model this pi as a function of the explanatory variables. Okay, so this part I think overall should be clear. I was not writing earlier, but in 347, what we did is you can think of and something happened. Okay, something. Okay, I mean, oh, okay, came back. Let me see. Okay. All right, so it's NP. Okay, so back then, what we were doing was this, that N is the total number of survey respondents, and P is the success probability. Okay, I'm trying to contrast here, we have PI, because now we have different observations. We're trying to model like a record level, and then N now is 1, because we're only looking at one outcome. Okay, and you know this probably as well, that sometimes instead of binomial, we talk about this as a Bernoulli trial, because Bernoulli is one single binomial, or I should say binomial is a collection of same Bernoulli, independent Bernoulli with the same success probability. So that's okay, I hope. All right, so the key here is if we're trying to model this Pi, we know that it's a success probability. It's going to be between 0 and 1, right? And we know that it's going to be continuous. Or if you want, I mean, at least we can model it as a continuous variable. So if it is continuous, that's, I mean, if you think about the normal linear regression that we did, the outcome is also continuous. But what's special there is that we don't really have a range of what this variable should go from where to where. Like it's almost like that y that we used to do, yi, if we're doing normal mu I sigma, something like that. When we're doing this kind of modeling, I mean, it depends, but remember when we take the log of the income or expenditure, if yi is the log of that value, then that value should just take like any value on the real line. Okay, so that's why, I mean, back then you can use a normal model. Of course, you can play with how you want to get the mu I and sigma, but at the end of the day, there's no much restriction of what this yi could be. But with pi, it's different, because pi, even though it's continuous, it lies between 0 and 1. So immediately you would think that, well, we probably cannot do a normal model unless you do a truncated, which we actually talked about in 347, if you remember. But for logistic model, typically people will do some transformation. So pi continues on 0 and 1. So the definition of odds is the success probability over the failure probability. So pi over 1 minus pi is going to be positive. Okay, positive continues. So still, we have to take care of the other half. I mean, other half of the real line if you want to do a normal linear regression type of stuff. So instead of working with the odds, people like to work with a log odds. Okay, so pretty much we're taking the log of this odds. It's going to be continuous, and it's going to be on the real line. Okay? This is very similar to what we did earlier here. If you are trying to take the log of some positive number, then you transform that into some quantity continuous on the real line, and then you don't really have much restriction in terms of modeling. Okay? So log odds ratio here is on the real line, and then soon you're going to see that logistic model is trying to create a linear function of this log pi over 1 minus pi in terms of the explanatory variables, and then we model from there. So this is the link, in some sense, from the normal regression to logistic regression. All right, so what you can do, so for simplicity, let's assume one explanatory variable xi, and then a linear function of xi for the logit of pi. Logit also, it just defined, I mean, people have different names for this, either logit of PI, the success probability, or log odds ratio. Whichever you use, it's going to be a linear function about the xi. Okay. So here, we're trying to use the information of xi to model the logit or the log odds ratio. And then in particular, it's going to be a linear function. Okay. And you see that, well, whenever you're working with linear function, you will have an intercept, right? Oh, sorry, you have, yeah, intercept here, and then you have the slope. Okay, so typically, because when you try to express something through a linear function with one variable, you will have an intercept and a slope. But if you have multiple explanatory variables, you're just adding them, as you have done for the multiple linear regression. So not surprisingly for Bayesian inference, if we have a model like this is my parameter number 1. This is my parameter number 2, right? I have 2 parameters. And in Bayesian inference, what we do is we specify priors for those parameters. We do the MCMC estimation. You can do it through JAGS. And then we will be able to get the posterior draws. Okay, so same story. Hopefully everybody feel familiar. And the last part I highlight here is in the context of what we're trying to do, the Bayesian synthesis, we don't just stop here when we just get the posterior draws, right? We should continue. And what we do is use the posterior parameter draws. We make posterior predictive distribution, right? So we can get the new y's, whatever you call y for. And then those, as you know, will be our synthetic data. Okay, so we did that for the simple linear regression or the multiple linear regression that you did. But here, things are not so much different. I just want to call your attention to this, that you can write the model in JAGS, do the MCMC estimation, the draws that you get from the MCMC using JAGS, they are the parameter draws. Okay, we have to do one step further to do predictions, and that prediction will become our synthetic data. All right, so for this, I included some sample code. I didn't run any of this. This is just like for you, if later when you're working on your project or some other things that you're curious about, you will be able to use a logistic model, and this will be the model string. Things slightly different from before. Some of you know this, especially, I mean, some of you were doing related topic for your project, so you know this. But anyway, so here you see the sampling part. What we do, we have a binary outcome, so you can use the dburn. Dburn stands for Bernoulli, okay, in R, in JAGS. And then remember, we have this yi independent of binomial 1 pi, right? So that's translate to this line. Okay, so that's the sampling model. But what's more here is, remember, it is about the logit of the pi, which is a linear function. Okay, and the logit function is readily available in JAGS, so you can just use it. And this translates to, if you remember, logit of pi equals to log of the odds ratio. Okay, and then we wrote this as a linear function of beta 0 plus beta 1 times xi. Okay, so that part of the model translates to this line. And you notice that the sampling, we loop through every observation, okay? And those 2 lines should be in this loop, okay? Because you're going through observation by observation. For priors, I mean, for simplicity, I put 2 normal priors here, and you can decide what you want for your mu0, mu1, and g0, g1. But really, I just put there as placeholders in the sense that in practice, as you know, it might be really challenging to specify these priors. You might get like super vaguely informative or like weakly informative prior, that's fine. But if you remember, and I'm happy to talk more about this if you have questions or like run into those, how you can do the actual estimation for the logistic regression if you're doing that for your project. I'm happy to like give a little bit like small lecture there about if you want to use the conditional means prior. So just to refresh your memory, we talked about conditional means prior back in the Bayesian course. And there, we're not talking about it under the context, in the context of the logistic regression, which is like the simple linear regression that we're talking about. And we were there like trying to do standardization of the outcome and the explanatory variable. And we're saying that, yeah, it could be really challenging to give prior directly to this intercept and slope. So what you can do is you can pick a particular, like 2 particular values that you have for the mu, like the mean that you're trying to estimate for the y's. And then you can specify prior, not on beta 0 and beta 1 directly, but on those 2 means directly. Okay, so the slides and stuff are still available on GitHub. I sent you the link, a different GitHub page of what the 347 material was. So I would suggest you to go to read that if you want. But the short story here is that directly specifying priors for beta 0 and beta 1 can be challenging, so you can use a conditional means prior if that's what you want. But of course, you can always give like a mean 0 and then super large variance if you want for beta 0 and beta 1, and then that will be very weakly informative. Okay? And then that usually will do the work anyway. Make sense? Okay. Yeah, so I think I included some a couple of slides on how to do synthesis from a logistic model. So if once we run our MCMC, we get the posterior draws of beta 0 and beta 1. Okay, so now how can I get my yi tilde? That's the prediction that I'm trying to do, right? So in order to do that, I'm listing here 3 and 4 equations. So again, if you look at this, if you think about the prediction process, naturally what we do is we get draws with beta 0 and beta 1, right? We multiply beta 1 with xi. These are given because these are the unsynthesized variables. So you get that, say for each observation x, like let's just say x1, you get a set of beta 0 and beta 1, right? So you'll be able to get this log p1 over 1 minus p1 for x1, right? And then from there, you will get the pi, and then from there, you are able to use equation 4 to do a prediction of yi. Right? So that's the logic, right? And what we could be doing is just, this is just like math that we need to know, like how can we get pi from the beta 0 plus beta 1 xi. So this is just the algebra that I included here. If you have your beta 0 and beta 1, and then your xi, then you're able to get your pi from here. Okay, and some of you, if you know about this logistic regression in the past, you will know that people always need to use this equation 5 to do any kind of interpretation of those parameters anyway. Okay, but for our purpose, let's not worry too much about interpretation. We get the posterior draws for beta 0 and beta 1, and then that's how we can translate into pi. And then from pi, we use equation 4 to get the prediction. Okay, so workflow wise, so I include this again just to make sure that we understand like the workflow in a sense that, remember, for the simple linear regression, there was some confusion about, well, what exactly, like how many draws I'm doing and all that. So from your MCMC output, because we run it long enough and then we want to check all of the diagnostics. So for example, we have 5,000 again. Okay, so you have 5,000 sets of beta 0 and beta 1. Okay, but then to generate one synthetic data set, we have to do that for all of the yi's. So that means you can use one set. Okay, you do that for every observation. Once you do that, you're gonna get a set of synthetic values for y1 to yn tilde. And at the end of the day, you're only using one set of the posterior draws. Okay, I think now we're clear. But just to show you the workflow, that's what you do. And then, of course, if you are going to synthesize multiple synthetic data sets, then you choose the particular iterations that you're doing. And so there are certain coding involved. I think I included, like a short script, like snippet of the code, how you can do it. So it looks very similar to what we did before, except here I'm using log p because that's what's being calculated for the log pi. And then I can transform it into p by using that algebra transformation that we talked about. And then you're able to use this R by norm. You see that we're only doing, so we're doing for all of them, and then for the probability. So all of this are vectors. That's why you can do it in one line. Okay, so you can play with that. So again, I didn't round any of this, so they should be fine. Maybe there are some mistakes, but if you see anything, you can let me know. So the input x is the vector of the unsynthesized variable, will be the explanatory. So we're only working with one explanatory variable, so it's going to be a vector. Otherwise, you might be able to do multiple predictors or explanatory variables that would just work in a similar fashion. Index, I'm using it in the same way as before, that it will just be which iteration they're using to do your synthetic data set. And if multiple are needed, you can repeat the process m times using m independent MCMC iteration. So once you do that, a set of synthetic binary outcome should be ready for you. Okay. If you do it multiple times, that will be what you're getting. Questions, comments? Familiar? Some of you I know have experience about this. So, but again, now we're always working with synthetic data context. So there's one extra step. But of course, when you have your MCMC output, like the posterior, don't forget to check MCMC diagnostics and all that. I know like many of you do it in the write-up that you do, but just for your project as well, or any kind of application that you want to do, make sure that it's sort of embedded. Like don't forget to make sure that the MCMC has converged and everything is fine. All right, the other type is categorical variables. We define categorical variable here, say it's yi, and then it takes values from 1 to capital C. Okay, so C stands for categories. I'm just using this notation. So examples include like marital status. Yeah, so in the ACS data, I think it probably has 6 levels. Yeah, and then race is another one. I think it appears in the CE sample as well. So there are many categorical outcome variables. And I think last time we talked about, yeah, what about we can turn some of the continuous into a categorical. So those, once you do that, you should model them as a categorical variable there. There's some caveat. So here, the models I'm going to introduce, they work with what we call, even though I call it categorical variable here, but really they are unordered categorical variable in a sense that there's no inherent ordering of the categories. Okay, like race. Yeah, it's hard to say, but yeah, I mean, it's hard to phrase this. Let's just use marital status. I mean, there's no ordering of like married or widowed and all that. So those variables, race, marital status, and many others, we call them unordered categorical variable. And then if you use a multinomial, it makes sense in a sense that, well, so multinomial random variable is an extension of binomial. So binomial, we know, Bernoulli, I should say. So Bernoulli, we know that only takes, like the outcome is only success or failure, right? There's 2 categories. So you only need like PI, which is the success probability, because once you do that, I mean, the other one, 1 minus PI will be the failure probability, add up to 1. But if you have multiple categories like this, or like marital status or race, when they're unordered, you can use this multinomial random variable or like model. You can pretty much have all of your, so P1 to PC, P1 to PC. We still have this I index here because it's observation specific, but it's PI1 to PIC here. So these are the probabilities of getting each of the category, okay? And they should add up to 1, okay? So for example, when you're working with race, this is just an example, we know there are 6 categories. So you might have for person I, you have PI1 to PI6, right? And then it's possible, I mean, maybe add, so you will notice like those are parameters that we have to estimate. So when you do Bayesian methods, you're gonna have MCMC draws for those. So maybe at 1 iteration, like at iteration S, you might have it, for example, I'm just making this up, but I just want to show you why they add up to 1. Which you probably have guessed anyway. So maybe it is 0.7, 0.2, 0.05, 0.05, 0.05, and 0.05. So this is the example of the 6 different categories. Maybe at 1 iteration of our estimation, I'm gonna have, like, say, for the first category, which I think is white, will be like 70%, for example, and then 20%, et cetera, et cetera. But make sure that they add up to 1, okay, in terms of the model, because you have to come from one of the 6 categories. Okay. but we might have a higher chance of coming from a particular category, things like that. Yeah, so that's what we mean. PIC is the success probability of the observation I taking yi to be C, that particular value, okay? Because it goes from 1 to capital C. And we also have this 1 here, so you're only taking 1 draw. So once you do your draw, your yi will just be a vector of like 0, 0, 0, maybe 1, then 0, 0, 0. Okay, it's going to be an indicator function to the category that you draw, and then everything else will be 0. Okay, and then lastly, they sum up to 1. The success, not success. The I should say category. Yeah, the category probabilities, they should sum up to 1 because you have to come from 1 to 1. Okay. So I mean, naturally, you might be wondering, what can we do about those PICs? We know that they have this restriction that they have to sum up to 1, right? It's not easy. It's sort of like it's tricky, and we have to think about ways to do that. So the 2 models I'm gonna introduce today. One is the extension of the logistic regression for categorical outcome. So the first one is called multinomial logistic regression. That's what people usually call it in the literature. So we're going to talk about that. And that kind of method is mostly used when you have explanatory variables, like you have some predictors or explanatory variables you can use. So you're going to see why that is the case. And the other thing for Bayesian inference in particular is that the multinomial random variable, the multinomial model itself, actually has a conjugate prior. Okay? The conjugate prior, if you look at what the variables are, I should say parameters. The parameters are all of those P1 to PC. Okay? It's a vector. They're probabilities. They should add up to 1. So it's going to be this whole vector of length C. What is it? Conjugate prior for that is a Dirichlet distribution. Okay, so we're going to talk about that as well. Mostly, you will see that when you don't have any explanatory variables to work with, you can use the Dirichlet-multinomial model because you're directly working with the probabilities. Okay. Whereas for the first method, you will see that we're still trying to figure out some kind of regression type of work that we are able to factor any kind of explanatory variables that you want into the setup that we do. Alrighty, so the first one is a generalization of binary logistic regression, and for illustration purpose, I'm also assuming 1 explanatory variable xi generically. So yeah, this is just like how the model is set up. Similar to the logistic model, we're also going to work with the log-odds ratio, but the log-odds ratio now is not just about the success over failure, because now we have multiple groups, right? So instead of working with that, what we do is you always look at the log-odds ratio. So there's some terminology. So odds, we know, like, so let me just finish saying. So for category C, relative to category 1. So you always have a reference category that you work with when you have multiple levels. So what we mean by, so the log of P, so again, this is on specific observation, so I keep that PI there. So log of PIC over PI1. So this is the probability of the observation I goes to category small c, right, by definition. The one in the bottom is the probability of the observation I goes to category 1. Okay, both of them are probabilities. We take the ratio, it's going to be positive, right? And then we take the log again to make it on the real line, and then that will be something we can model. Okay, so if you look at the right-hand side, we have a linear function, very similar to logistic regression here, but notice that we have many more parameters now, because if you look at beta 0 and beta 1, they also have the extra subscript about C, because it's for each category C. So what that means is if we have race again, if we have 6 categories, except for P1I, right, a PI1, we're going to have PI2, PI3, PI4, PI5, and PI6. Okay, so that means for beta 0C and beta 1C, we have to have it for C from 2 to 6. Make sense? Just because how the model is set up. I mean, again, mentioning this or like highlighting this because, well, this is going to get into our way. Well, like going to become like challenging, or like we at least should keep in mind that we do not only have two parameters. We have 2 times how many levels minus 1 that you're going to have to model. Okay, so there are 6 categories that we have for race, but because like the first category, category 1 is the reference level, so you don't have to model that. You need to model like C from 2 to the maximum category that you have. So in the race category, in the race example, you're going to have that for each category C, and then you're going to have 5 of them. So of course, as you can see, if you have a categorical variable with many, many levels, the model just becomes more complicated. In a sense that you have more parameters to estimate, meaning that it's just going to become like slightly more challenging in terms of computation. As well as, well, we have to make sure that we keep track of all of the stuff that we're working with. Okay? So for Bayesian inference, not surprisingly, you give prior for those parameters, do JAGS estimation of MCMC, and then you get posterior draws. Then for synthesizers, we have to use those posterior draws to make predictions later. Okay, so similar to logistic, but now you have multiple categories, so we have to be careful about that. All right, so let's just see. Also, just as you know, later when you're trying to do predictions, we want to get the p, not the log, like PIC over PI1. So you have to do this log not log transformation. You have to do the algebra to get it back. Okay, so I included here because this will go into how we're gonna write code to do the synthesis. So model stream, I don't think I'm gonna spend too much time on this. You will see this new D multi, so that's the multinomial distribution, okay? And so that one stands for I'm only making one draw, okay? It's the last argument in terms of how JAGS was written, so that's what it is. And here, as you can see that my P, it's gonna be a big vector, big matrix that we're working with. Each row is an observation, each column is for a particular category C. Okay, so that's why I'm writing, so let me just do it here. That's why we here have PI when I'm writing for YI, but then I have to get all of the columns here, okay, because I'm doing a multinomial draw over all of the category probabilities. And then we have to write another loop inside this loop just because we have to get all of the PI working. So this is from the previous slide about that algebra transformation that I said we have to do in order to get P. So I'm using Q to represent the exponent of that function. And lastly, it is the log of this is the linear function. Okay. So after class, you can definitely spend time looking at back and forth to make sure you understand it. And let me know if you see any mistakes. Again, I didn't run any of this. I just put it together for the lecture. So there might be mistakes, like say typos, I don't know. And then here, this is how you're gonna get the prior, okay, as an example. So different priors you can use, and that will be something you can use if you are trying to model and synthesize a unordered categorical variable. Right, so there's some explanation you can take a look afterwards. So the last one, the Dirichlet-multinomial model, this is I think this is probably the most intuitive because this is conjugate prior, okay? So this is, you can think of it as, remember the beta binomial that we did in Bayesian class? So we derived it back then, that beta will be a conjugate prior for the success probability of binomial. They're all univariate because it's success like P, and then that is the variable that we model using the beta prior. And then in binomial random draw, like P is the univariate success probability. Here, everything is multivariate in some sense. So we're still going to have the sampling model here, which is the multinomial, and it's going to be PI1 to PIC. We saw that, and like we were talking about earlier, all of these are parameters. Okay, and we have for all observations. So n is small n is the number of observations. So just a little bit convoluted, but equation 9 here. Once you do the math, you will get it. It's not that complicated. but you will be able to write the joint likelihood function of the parameters. Okay, and one thing you notice that is we didn't do much about this product. So this product comes from the fact that observations are independent from each other, right? So I'm producting over all of the observations. Inside is the likelihood function for each of the observations. Okay, and in the end, I can write out my likelihood function in this way. You can just leave it there, and because for posterior analysis, if you want to get the analytic solution for conjugate cases, you will write the likelihood. So now we have the likelihood function. You will also have the prior distribution with, it's going to be Dirichlet distribution we're going to talk about. And then you combine them, you will come to the posterior. Okay, so this is the likelihood. And the prior, don't worry too much about it. It's a Dirichlet distribution. But you will see that the kernel look very similar to what the likelihood is like. Okay, so that, again, gives us a hint of why we probably gonna have a conjugate result in the end. Okay, so the joint prior looks like this. So again, we have the product first about different observations. The second product here is about like different categories. Okay, and then it's producting together. But that will be the parameter that you have, hyperparameter you have here. This, in some sense, looks very much like beta, if you remember what beta looks like. Beta is like p to the power of alpha minus 1, right? And then 1 minus p to the power of like beta minus 1. They have two parameters. Hyperparameters here is only one. But from the form, you will see that they look very similar. So when you do your conjugate analysis for the posterior, it's going to be a Dirichlet. That's why we mean it's conjugate, because you start from Dirichlet, and then you end with a Dirichlet. So it's conjugate. And the parameters, you know what? Looking at each category here, actually will just be the sum. Okay? And sum of what's from the prior and what's from the likelihood. Okay? So so this again ties back to the beta binomial, but everything works in a very similar fashion. So I would just recommend you to, in class, get the big picture of why we're doing this. But then after class, or if you're trying to implement this, you will see how things are related to each other. So they also include the JAGS script that I wrote. You have the D-multi, that's for the multinomial likelihood, right, sampling model. And then the D-Dirichlet, that's the prior that you have. Okay, and then lastly, you're going to have the other ones for those. Make sense? Make sense? Yeah, it's a long lecture, so I hope you're not falling to sleep. But we're just trying to cover different types of variables, what you can do about them. And this will be a